Well, thank you very much for the introduction. And I owe a special thanks to Lillian Pierce and Damaris Schindler, who I think have been extraordinarily courageous in organizing such a big meeting and helping to create this accident of a joint session. I think it's already a success with a big meeting if there are no disasters, but there's been nothing resembling a disaster so far, at least, so I think this is a great success. It's certainly a great pleasure to be here in one of my favorite cities in the world. Good, okay. So when I heard that I would be speaking in a joint session, it helped convince me to be a little brave myself. So I'm talking on this topic which I've been thinking about. I was motivated by the archive preprint, which appeared earlier this year by Bourgain and Demeter. And this is still work in progress in the sense that I don't know how far this will go, and there's still many ideas to explore. But at least it gives me an opportunity to explain how this is connected with recent progress on Vinogradov's mean value theorem and this new method, efficient congruencing, for estimating this. So first of all, I can tell you a bit about sort of background and motivation, which allows me to go backwards in time to things I used to think about more than 10 years ago. So let me define, and I'm calibrating my writing. I will probably get smaller and smaller, so if you're at the back, you need to shout when it becomes unidentifiable. Okay, so let me define the number of solutions of a system of Diophantine equations. And these are equations, they're not inequalities. So what I'm interested in for the moment is the number of solutions of a pair of equations. And I'll write them like this. And I hope that I get to efficiently use these later on. So I have one equation of degree k. K is an integer which exceeds 1. And for the moment, just to keep things simple, I will slice this with a corresponding linear equation. So here are my two Diophantine equations which I want to study. And then I'm counting solutions where all the variables are at most b in size. So b is some large positive number. And so this is a counting problem. I'm counting integer solutions of these equations. So just to emphasize, x and y are integers. And this integer k is at least as big as 2 for purposes here. And this is a very classical problem. It's cropped up many times. So really a classical result. And I'm not sure who was the first to investigate this. I mean, in some sense, the situation where k equals 2 could really have been a 19th century result. Certainly, Hua investigated this in the 1940s. So it's known that when k equals 2, the number of solutions is asymptotic to a constant times b cubed log b for large values b, and the constant is even 18 over pi squared. And the very precise asymptotic formulas available these days, thanks to Bourgain and Blomer, or Blomer and Bourgain. So the latest paper is 2010, and there's an asymptotic formula with lower order terms available. It's quite impressive. But okay, so when you're dealing with problems involving sums of squares, classical machinery is available, and one expects to do quite well. We know a lot about problems involving squares. So then, if you're interested in how about that? How about that? Good. If you're interested in degrees larger than 2, then life gets a bit more interesting, a bit more difficult. So the first result that I know of in this direction is due to Hua. And I suspect Hua had this before 1947, but it certainly appears already by 1947. So if you're interested in the corresponding problem involving cubes, then it's possible to obtain an estimate which is big O of b to the 3 plus epsilon for any positive number epsilon. And in fact, what Hua proved was a result of this type where there's even an explicit power of log b here. I think it was log b to the 9, if I remember correctly. And this is a result which has been rediscovered many times. So certainly Both Bourgain and Heath Brown made use of this result in the 1980s. And this is a result which has been refined. So there are a number of obvious solutions to this system of equations. So if I take the x's to be a permutation of the y's, then you get a contribution which has order of growth 6b cubed. And then you can measure how many solutions there are other than these obvious diagonal solutions. So these are the ones where x1, x2, x3, written very small so nobody can see it at the back, is a permutation of y1, y2, y3. And then the other solutions contribute something which has order of growth, which is b squared log b to the 5. That's something that Vaughan and myself proved in 1995. Well, it got published in 1995. And then, rather spectacularly, there's even an asymptotic formula for this secondary term, which has been proved more recently by de la Bretèche. Who's in the audience who can tell me when it was published, but it's written down here somewhere? 2007. Ah, yes. No. Second one is okay. That one is okay? Okay, good. Recovering myself a little. Yeah, so you can see, I mean, this is something which I labeled as a sort of, I tried to describe as a paucity result, because the obvious diagonal solutions and then the number of non-diagonal solutions has order of growth which is definitely much smaller. So almost all of the solutions of this equation, when k equals 3, are diagonal, which is definitely not the case for the case k equals 2. And this, in fact, is a general phenomenon. So if you look at the situation where k is greater than 3, and here I'm not aware of any result until the early 1990s, although it would have been easy to prove something. So in this situation, it's fairly easy also to show that nk of b is growing no more rapidly than b to the 3 plus epsilon for any positive number epsilon. And the trick, if you want to sort of think about this as you get bored later in the talk, or maybe instantly, then the trick is to use the factorization that there are two very obvious linear factors using sort of polynomial identities coming from the system of equations here. So there's sort of linear factors x1 minus y3 and x2 minus y3 when you look at this difference between something that you can see appearing in the equation here and subtracting the kth power of a corresponding linear expression. And so you get sort of divisor sums appearing. And if you work harder, you can even get paucity results here as well. So the sharpest estimates, well, maybe these are not the sharpest estimates anymore, but certainly you get the obvious diagonal solutions, and then you can certainly get an estimate at least as good as b to the 17 over 6, which is smaller than 3, plus epsilon for the number of off-diagonal solutions. So this is something that George Graves studied in 1997, and Chris Skinner and I also have a result on this, which is slightly better when k is larger than about 8. Okay, so you can see there's sort of a nice family of results, and actually similar results even if you investigate what happens if you don't have a linear expression here, but something of higher degree. You have these paucity results where the bulk of the solutions are diagonal. And somehow you can't escape from those diagonal solutions. They're definitely there. So we understand fairly precisely what happens with the number of solutions of these equations. So what next? So that's where this paper of Bourgain and Demeter comes in. So the title didn't suggest any relation to these equations. But I looked at it anyway because I like looking at interesting papers, and inside the paper was this, what I thought was an amazing application, which is very much related to this system of equations and other systems of equations and inequalities as well. So this is, you can identify this on the archive, and if you were at an earlier talk, you probably even have an archive reference for it. I have an archive reference for this. Okay, so here we are. Good. So let me define a modification of the counting function which we were just looking at. And so now, instead of having these two equations, I'm going to replace one of them by an inequality. And the inequality certainly contains the solutions that we were just looking at. So okay, I'll say a little bit more about the terms appearing here in just a moment. Okay, so here's my inequalities. Just think of C as being a fixed positive number. And again, count solutions, but this time count solutions which are in a dyadic interval of size roughly b. So when I write the twiddles, this is what I'll mean. Okay, so obviously, although, of course, in the top problem, I'm counting solutions in a box where the variables are allowed to be as small as they like. In this problem, they're restricted to this upper range. But this system of an inequality with a linear slice captures solutions from the pair of equations there. In fact, it captures them because there's this thick neighborhood around the solutions of the equation. So you might think that there may be many more solutions, especially if k is large. And what's remarkable about this theorem, I'll call it theorem A, is that the number of solutions here is still less than b to the 3 plus epsilon for any epsilon greater than 0 when k is at least as big as 2. So you might imagine, okay, so when this is 0, maybe I capture the same number of solutions as above, about b cubed, but maybe I have a chance to capture lots of other solutions for all these other different possible choices for the right-hand side. But still only have b to the 3 plus epsilon solutions. Fantastic. Okay, so should I feel impressed by that? Well, we should ask ourselves how many solutions to expect. Well, I was impressed, but then I had to think whether I was impressed or not. Of course, I mean, your expectations are conjectures. They're not mathematical proofs of anything. But the two types of solutions, in a similar sense to the two types of solutions of the top system of equations, the diagonal solutions, where the, such as the solutions where the x's are diagonally equal to the y's, and obviously the number of solutions there has order of magnitude b cubed, same as before. And those are very special because in these solutions, this expression is actually equal to 0. So we're counting the same solutions as we saw above. And then there are non-diagonal solutions. And these are always the tougher ones to think about, well, usually. And for non-diagonal solutions, how many should we expect? Well, let me see. Right. So we've got b to the 6 possible choices for all of the variables. And there are some constraints on these variables. So, of course, on one side, we have this linear constraint, which is going to reduce the number of solutions by a factor b. Even we can see that. That's linear algebra. That's no problem. But then we have this inequality as well. Now, because the variables are of size roughly b, this expression might be as big as b to the k. But in fact, we're restricting it to be at most b to the k minus 2. So in some very optimistic randomized sense, you might expect that we've got some kind of constraint of size roughly 1 over b squared at work here. So you kind of expect that the number of off-diagonal solutions might also be of size b cubed. So this result is pretty close to best possible. I mean, it's impressive. Yeah, I was impressed. Even after thinking about it for a bit, I was impressed. Okay, good. So, so far so good. So let me mention another problem. I'll call this theorem B, which has similar flavor. Okay, good. Okay, so theorem B. What's theorem B? So at first glance, you might think this is some kind of isolated result, and theorem B suggests that that's not the case. So now let me call nk plus of B the number of solutions of a different system of equations, or inequalities. So this time I'll have also the sum and difference of kth powers, but I'll be slightly less strict about the inequality, so this time it's growing like b to the k minus 1. And again, I'll stick with the, well, this time not a linear equation, but a quadratic equation. So that's my system of inequalities and equations. And again, these variables are all going to be of size b. Okay, so this time we thought about this a bit. We know what to predict, maybe. So our prediction, this is supposed to be a theorem. Our prediction down here, we're going to guess the answer. Well, we expect to have b cubed diagonal solutions. And then the number of off-diagonal solutions, b to the 6 choices for the variables. We have this quadratic equation. So even we could count the number of solutions, it's going to grow like b to the 4th. So we've got a constraint of size b squared. And now this constraint, if we're optimistic about what kind of constraint this should provide, well, we've sort of got a constraint of size 1 over b. So again, we expect about b cubed solutions altogether. And the theorem is that nk plus of b is less than b to the 3 plus epsilon as well. And again, I should say that the relatively recent literature as well. Okay, when I say recent, and I talk to my students and I talk about the 1990s, they look at me and their eyes roll. So in 1992, a result of this flavor was proved where this was actually an equality rather, equals 0 rather than this inequality. So again, we've got this thick region around the intersection, which is defined by these two equations. And still, even though we're looking in this thick region, the number of solutions grows like little more than the diagonal solutions. Okay, so that's all very good. I was excited. So I can tell you now the connection with efficient congruencing. So this is connected with Vinogradov's mean value theorem. So maybe, because I know I always run out of time, I should actually tell you some results, some theorems, and then try to explain what Vinogradov's mean value theorem has to do with this. So maybe I'm itching to erase something, but yes, okay, maybe I'll use the left board here. Is the left-hand board here visible for everybody? Yeah, you don't know yet because I haven't written anything down. Okay, so now I'm going to look at something else, which contains these as special cases. So I'm going to define ns of b, and there's a vector of exponents k. And this is going to be the number of solutions of a giant system of inequalities. And what does a system of inequalities look like? So I have now 2s variables altogether, whereas before I had 6 variables altogether. And the inequalities have exponents kj, So the k sub j's are going to be distinct positive integers. And I'm going to bound the absolute value of this expression by some constant. Again, it's going to be a fixed constant greater than 0, which I'll try to ignore, times b to the k sub j minus j. And how many of these inequalities are there going to be? Well, that's something I get to decide, so I'll call it t. And as before, the variables are going to lie in a dyadic interval of size b. And it's worth making a conjecture about what we might believe the number of solutions should be. And using the same principles as we had when I was discussing this just a moment ago, I mean, obviously there might be diagonal solutions. And the diagonal solutions would contribute b to the s all the time. And then there's the possibility of these off-diagonal solutions, which somehow you're predicting by assuming everything is nicely distributed and sort of random in some sense. And if you think about the total size of the constraints this time, well, there are b to the 2s variables altogether. And then the size of the constraints, I've got a constraint of size 1, b to the 1, and b to the 2, all the way up to b to the t. So that's b to the half t, t plus 1 altogether. And maybe, because we're always kind of pessimistic, we throw in an extra b to the epsilon just to be on the safe side. It's good to be on the safe side when you've got the system with exponents 1 and 2, for example. Okay, so that's what we might conjecture. And then you can see as a special case of, as a special case of this counting problem. So theorem A corresponds to what happens when s equals 3 and t equals 2 and k1 equals 1 and k2 equals k. Now you might complain that k1 equals 1, what's going on with k1 equals 1 with this inequality, whereas I had an equation before. Well, if I'm counting solutions where the absolute value of the difference is at most a constant, that's basically the same thing as counting what happens when you have 0 there. It's essentially the same problem. You can easily recover the same estimate in that situation. And theorem B is the same story, so s equals 3, t equals 2, but now k1 equals k and k2 equals 2. Okay, so both of these theorems are covered by this kind of setup. And then maybe I can tell you what the main theorem is. And I emphasize again, this is work in progress. I mean, when I was preparing the notes, I wrote down the most general assertion of this type. And when I realized that most was really excessive, it's certainly a more general assertion, but not the most general assertion. So there are many other things one can imagine doing. But certainly, what can one prove? So when do you have this conjecture? So maybe I should say when s is at least as big as t times t minus 1, then this counting function is bounded above by the second of the two terms. So this sort of randomized, but really it's a product of densities that is determining what goes on. And remember, a number of situations where you can say that the diagonal contribution definitely dominates. Is this definitely visible to everybody? Yeah, not really. Okay. Okay, so when does the diagonal solution dominate? Well, in three situations. So you have a diagonal contribution, b to the s plus epsilon, for any positive number epsilon, when... Okay, so here are the three situations that I know about so far. So s equals t plus 1 and t at least 2. Secondly, if t equals 3 and s is at most 6. And thirdly, if t is large and s goes up to 1/2 of t times t plus 1 minus 1/3 of t plus little o of t. So maybe I could. I guess as you get older, you get weaker. I'm still weak. Okay, so I won't use the third board. So maybe I should say, I mean, case B there, t equals 3 and s at most 6, you might wonder, why on earth did I write that down? Well, this is actually a best possible result. So somehow, knowing that you have this diagonal behavior when t equals 3 and s is at most 6 actually implies the whole of the conjecture, in this case where t equals 3. So if you have not 2 exponents, or 2 inequalities, but 3 inequalities, then we know everything about that situation. We can prove everything that would be conjectured. When t is large and s is almost as big as 1/2 t plus 1, then again, we're getting this diagonal contribution. Somehow the limit of that diagonal behavior would be 1/2 t plus 1, if you just think about the conjecture. So again, you're very, very close to proving the whole of the conjectured estimate. It's sort of on the edge of proving everything that you might want to with this inequality problem. And there is a connection with Vinogradov's mean value theorem, which is what I want to explore now. So Vinogradov's mean value theorem doesn't have to do with inequalities like this. It has to do with systems of equations. And the equations have a special shape. Maybe. I guess it stops automatically, yeah. The equations have a special shape. So what you have is a system of equations where the exponents are consecutive from 1 up to k. And it turns out that this is a translation invariant system, which is important for the methods which are available. But, and I should say these are things which have been studied for 80 years. And the sort of the culture in the subject is that these estimates are really pretty good, but they weren't best possible. And recently there's been progress which makes them essentially best possible. And that's key to this new material. So here's Vinogradov's mean value theorem. And I just want to give a very rapid digest so that I can give a flavor, hopefully within my time, of some of the ideas that go into proving these new estimates. So what's going on in the subject? Well, we have an exponential sum. So here's some notation for this. So I'm summing over integers between 1 and a large positive number, capital X. And the argument of my exponential sum is a polynomial of degree k with real coefficients. And as usual in this kind of subject, I write e of z for e to the 2 pi I z. And the mean value, which is central, is, well, I call it, you can call it, you should call it this as well. I call it JSK. Oops, front one. Right, so JSK of x is just going to be the integral over 0, 1 to the k, unit cube, of fk of alpha x to the 2s. And by orthogonality, this is counting the number of solutions of a system of equations, and that's, you can see one connection already with what's been going on above. And the system of equations has 2s variables altogether, and exponents 1 up to k. So superficially, it resembles the kind of setup that we started with. And then these variables now run up to capital X. And maybe it's worth saying, it is worth saying, so theorem, which is the classical version of the subject. And this all started with Vinogradov in 1937, 35. And there was a long sequence of developments, and Hua and Linux and Karatsuba and others played very significant roles in this. So the final version of the theorem, dates back to maybe the late 70s or thereabouts. And what does this theorem say? Well, when I'll state it like this, and we'll interpret in just a moment. So if you suppose that SR and K are natural numbers, and S is at least as big as R times K, so it's a multiple, it's at least as big as this multiple of K, then you have an upper bound for this mean value, which has dependence on the parameters R and K. And we don't really care about that dependence, so there's some constant depending on R and K for which this inequality holds. And the exponent of x, which occurs, well, the x to the 2s choices for these variables altogether, but you do better by a half times k plus 1, but not quite. So there's an extra term which decays with R, or equivalently, if you like, with S. So this sort of difference between what is really analogous to the sort of a probabilistic sort of argument that we had with the inequalities, the difference basically looks something like k squared e to the minus s over k squared. That's the way to think about it. So when s is larger than k squared times log k, maybe times some big constant, then this discrepancy between what we would have predicted and what you actually get in the exponent is exponentially small, can be made very small. But if s is still a constant times k squared, that's still fairly significant. Okay, so that's sort of a classical picture. And then very recently we've gotten extremely close to the conjectures from this subject. Good. So I should tell you what the conjectures are. And then you'll recognize that there's a lot of commonality with the theorem on inequalities, which I just described. And there's no accident to that. So the main conjecture in this subject, by analogy, I don't think I really need to explain any more than saying that by analogy with what we described about or discussed about inequalities, is that this object jsk of x should be bounded by x to the epsilon times x to the s plus x to the 2s minus a half times k plus 1. So you've got the diagonal solutions and then this sort of probabilistic notion of what should happen with all the constraints imposed by the equations. And then, so this is sort of a theorem which summarizes consequences of this new argument, this efficient congruencing argument, which tells you that we're now really extremely close to proving the whole of this conjecture. So the main conjecture holds when, and here are some cases when it holds. So while k equals 1 and 2 are sort of classical, and then finally we have some higher degree situation where these conjectures are now known to hold. And then, which actually, I mean, I just write down 3 kind of casually, but that's a big deal. I mean, it was a big deal for me anyway. I mean, it's exciting to be able to do something for degree larger than 2. So also, the main conjecture holds and is dominated by the diagonal behavior up to a limit which I'll call d of k. And you can say what this d of k is. I mean, Presumably, with extra work, one might be able to extend these numbers a little bit, but just to give you a sense that we know something about what happens in general. And then when k is large, this number can be taken to be a half of k times k plus 1 minus 1/3 k plus big O of k to the 2/3. And again, if one could remove this 1/3 k plus the little bit here, that would actually allow you to prove the whole of the main conjecture in full. So for large k, you're really close to proving the whole of the main conjecture. And finally, if k is at least 3 and S is at least as big as k times k minus 1, then also this sort of product of densities dominates, and that's really provable in this situation. And presumably, in reality, you should be able to replace this bound by a half of k times k plus 1. Just so happens that when k equals 3, these two things are the same thing. So you might spot some similarity between everything with k there and everything with t here. So that's not at all accidental, as I said. Okay, so what can I tell you about how Vinogradov's mean value theorem is connected with these estimates on inequalities? And I can tell you something about that, which I'll try to do. Not as much as I would like, but that's how time goes. Well, there's a key property to this Vinogradov system which allows one to generate very good estimates. So it's key to getting the classical estimates, and it's also key to these new methods. And the key property is the translation, dilation, invariance. And maybe I'll use a small board just to say something about that, if that's visible to some people. I'm stronger on the right-hand side, apparently. Okay, so the key property is this translation, dilation, invariance. And let me just observe that if I have S tuples x and y and their integral solutions of the system of equations x1 to the j plus x2 to the j up to x sub s to the j is equal to y1 to the j up to ys to the j. And this is true for all j's up to k. So that means it's a solution of the Vinogradov system, what you can see there on the middle board. Then, for any shift xi, so this is an integral shift, and any natural number q, you have that xy is a solution of sort of a modified system, and this modified system is qx1 plus xi to the j up to qxs plus xi to the j is equal to the same thing with y's. So this gives you a way of going between basic solutions of a system and understanding what happens on arithmetic progressions. So if you're studying the solutions of this system where the variables are restricted to a given arithmetic progression mod q, then you can understand these solutions in terms of the solutions of a corresponding system where the variables are in shorter intervals. And that's critical to developing congruences which make these mean values, make it possible for these mean values to be estimated. So I can just say a little bit about that, show you where the congruences come from, and then I'll say a few words to show how you connect these inequalities to these systems of equations, even though they're certainly not translation, dilation, invariant. Okay, so just a little bit of notation, and then I'll sort of try to give you a clue about what's underlying this. So here's some notation. I already hinted that arithmetic progressions are important. So I'm going to define an exponential sum which has variables restricted to an arithmetic progression. And there's going to be a modulus involving a prime number p and a power p to the c here. But it's the same argument of the exponential sum. And then there's some other exponential sum which I just write down in order to be relatively honest about what's going on. And this involves an R-tuple of shifts, and the R-tuple is sort of being summed over possibilities modulo p to the c plus 1, and these guys are distinct modulo p to the c plus 1. But all of these things are congruent to the same c modulo p to the c. And there might be some other mild conditions which I'm sort of ignoring in order not to be too obtuse. Okay, so this is a bit like having R copies of the exponential sum, which is restricted to the arithmetic progression, with some mild conditions. These are sort of non-singularity conditions. And it turns out that, is it this one? Yeah. It turns out that that JS, this mean value which we're interested in, can be related to mean values involving these expressions. So I'm going to look at not JS, but JS plus R. So R is going to be fixed between 1 and k. So choice of parameters. And this mean value can be related to a new mean value, which I'll call IAB of x. And it's sort of a max over possible arithmetic progressions of an integral over the unit cube of something involving these sort of nicely behaved generating functions. So there are essentially 2R of these. And then other generating functions restricted to a different modulus with 2s of them. And what I want to do to give you a flavor of what goes on is just to think a little bit about what goes on in this mean value here. So it turns out that from the translation, dilation, invariance, you can create a strong congruence condition for the variables from this, which, I guess I have space here, don't I? So, so if we use orthogonality to interpret this mean value in terms of numbers of solutions of corresponding system of Diophantine equations, then what this is doing is counting solutions of what system of equations? Well, it's a system of equations which looks like this. So there are 2R variables which correspond to the fancy set of variables, the ones which are sort of non-singular. And then there are a whole bunch of other variables corresponding to the 2s choices here. And these ones are restricted to an arithmetic progression modulo p to the b. P is a parameter, is a sort of choice of prime which we have some liberty in choosing. Okay, so this is invisible to some people, but never mind. So you get the idea. So these variables are now in this arithmetic progression modulo p to the b. And I mean, these variables are restricted in various ways. So certainly all of them between 1 and x, if you sort of include the factors p to the b and eta. And there are some mild conditions on these variables. So xi and yi are congruent to c modulo p to the a. But this sort of thing we can ignore for the purpose of this discussion. So what I want to just observe, which is key to the Vinogradov method, is that from the translation invariance, the translation dilation invariance, we're at liberty to shift all of the variables by the same quantity. So I can shift all of these variables and still retain the equivalence of the solutions. I can shift by eta here. So if I shift by eta, then somehow these variables are shifted by eta, but eta has disappeared from the system of equations. And that means by the homogeneity, that's the dilation invariance, that this factor p to the b can sort of be extracted. And so now what I have is a new system of equations which generates for me a system of congruences. So the translation dilation invariance, what it does for me is to take me from a system of equations restricted to arithmetic progressions to a system of equations, a system of congruences modulo p to the jb, for j running from 1 up to k. And so when I'm counting solutions of a system of equations, I can make use of the fact that a set of these R variables, two R variables altogether, are constrained by the strong congruence condition. And in fact, if I insist that R is not too big, you can see this already. If R equals 1 straight away, this already forces a very strong constraint on the variables. Xi will be congruent to yi modulo p to the kb, or pretty much so. So if R is no bigger than about half k, the number of solutions of a system of congruences is essentially big O of 1 modulo p to the k minus r plus 1b, pretty much. So you have something resembling sort of diagonal behavior for the congruences. And so what this means is that you can very quickly, you can use this to get a concentration effect which allows you to estimate these mean values extremely efficiently. So it's a sort of an iterative approach to doing that. So what I want to do just in my my overtime, if I can, Okay, I'm not doing well. Here we go. No, that's still not well. Here we are. Okay, in my overtime, if I can use 2 minutes of overtime, I can give you the clue about how you actually attack these systems, which are obviously not translation dilation invariant. And so, I mean, there are several problems. In fact, I mean, at first glance, it looks as if you have no hope at all, because these inequalities are not homogeneous, because they're inequalities. They're not translation invariant, because you don't have all the sets of exponents. And in terms of the part of the efficient congruencing method, which I haven't described, the lack of translation invariance also means that you don't have a nice way of going from sets of solutions on an arithmetic progression to sets of solutions on shorter intervals. So there are several things that one has to address there. But still, roughly speaking, what goes on? So there are several ingredients. The first is, obviously, the inequalities are not very good for understanding in terms of congruences. And so what you have to do is go back to the original Vinogradov method, one which, if you study older textbooks like Titchmarsh's book on the Riemann zeta function, this is how you learn about Vinogradov's mean value theorem. You use short intervals instead of congruences. And the whole of the efficient congruencing method can be converted so that you're only using short intervals. And if you're a number theorist, this isn't such a big deal, because it's just like shifting the that you're working with from a finite place to the infinite place. So that's not a deal breaker. The second observation is that when you have these different exponents, which may be spaced apart, you're trying to understand what happens when you have terms involving kjth powers of representatives from these arithmetic progressions modulo p to the b. And you have a whole bunch of these expressions, t of them, but you can use the binomial theorem plus linear algebra to come up with an equivalent system of inequalities where you actually have a sort of a Vinogradov system appearing inside the inequalities. So you'd actually convert this to a system which involves, well, let me write it this way. So you've got some sort of fixed coefficients. And various powers of p. So there'll be a p to the jb here, and an extra p to the b, and so on. So everywhere where you see a p to the b ui plus eta to the kj, by using linear algebra, you can sort of kill off linear terms from most of the inequalities, and then quadratic terms, and so on. And you end up with a system which is, at least in the congruence setting, is approximated by a Vinogradov system, exactly the same Vinogradov, but with an error term. So in terms of congruences, this is a p-adic error term. In terms of short intervals, there's an analogous result. And so that means that this method, which on the top board is using translation invariance to generate these strong congruence conditions, you still get to do that. It's just that the congruence conditions aren't occurring with modulus p to the kjb, but just p to the jb. But we still have t of these congruences, and that's why in all of these results they look very much like the Vinogradov mean value theorem results, but with t in place of k. And then the third thing, which I won't say anything about for lack of time, is to get over this problem about how you relate what happens in arithmetic progressions to shortened intervals. And there's a sort of a way of maximizing over possible choices of coefficients, which actually allows you to basically work in the same way as before. Okay, so definitely I stop there. Thank you.